Hi, we're the 5G Next group. I'm Ryan. This is Aleksa, Stanislav, Sreeram, Nikhil, Sanskar, and Jeff. So for our project overview, our goal was to develop an open source implementation of a 5G network, and within this network to create network control and management applications that are developed for things such as security, resiliency, or for spectrum sensing, and to also develop other framework services that would work with this network. And this is all done in the context of ORAN, which I'll get into in a bit. Is it? Okay. So for our network, we have UEs at the bottom, which are user equipment, so anything that can connect to the network. Okay, those connect to RUs, which act as antennas, and then it connects to CUs and DUs, which would be responsible for more baseband processing. And at the top, we have SMOs that would stand for service management and orchestration, which would be responsible for managing the rest of the network. And that's where we develop most of our applications. And this would be the radio access network. So this would be where we would do most of the implementation, and then the SMO would control most of it.
So for our implementation, we are trying to establish an end-to-end connection between our UE and the internet through general purpose hardware and also open source code such as Open Air Interface, otherwise known as OAI. So to test the network, we use a UE SIM code called Amarisoft, or we also use Android phones to test the performance of the 5G core and Geno B on one of the Cosmos test beds or nodes. And primarily the way we actually establish the physical connection between our software network and the phone is through a software defined radio, which is otherwise general purpose hardware that digitizes radio functions such as modulation through software instead of customized hardware. And that allows us to establish open source implementations of a 5G network without specific radio components. Next slide. And so for our actual results, we were testing on a OnePlus 8T, which can be also remotely accessed. For our results, we were able to get an 18 megabit per second downlink and a 15 megabit per second uplink for the phone. And on the right, you see a core CU, DU, UE through SIM 8200 implementation. The SIM 8200 allows us to basically test out a SIM card without necessarily using the features of a phone. And for that, we were able to get 11 megabits per second, primarily because the DU had a buffer size that prevented higher data transfer.
So shown here is a block diagram representing the functions in our system. So in the blue is the SMO, and in red are the SMO applications that we developed for security, resilience, and spectrum management. And then we also have the topology service, which we developed. And all of these functions communicate through the Orbit AMQP or Advanced Messaging Queue Protocol server. And these will all be discussed more in future slides. So shown here is a sequence diagram developed using Plant UML to represent the exact data flow and messages being sent between our functions. It's probably difficult to see right now, but this same diagram will be on our poster as well as on our website.
So as seen over here, we have the topology service. The main responsibility of the topology service is to hold the master copy of the topology, which it can send as an initialization to all the RApps whenever required. It also receives the changes or the deltas from the other RApps so that it can update its topology, and all the communication regarding changes in the topology should be communicated to the topology service. Apart from this, as shown in the diagram over here, we can have the topology in which a UE is connected to multiple RUs or an RU is connected to multiple UEs, as well as having an RU which is not connected to any UE at all. This is the resiliency RApp. The main responsibility of the resiliency RApp is to find the optimal distribution of data among the multiple network parts that are possible. As seen from the diagram over here, let's assume that a UE is connected to 3 different RUs. The red path is lower security and lower cost. The blue path is high security and high cost. And the green path is the average of both cases. So let's say that for a given requirement, the user wants a higher security path. In that case, we can select the blue path. And if we want to send the data cheaply, we can select the red path. And the resiliency RF will take care of this automatically based on the metric that has been provided to it. This is the output of the resiliency RAP. As we can see over here, the resiliency RAP is connected to the RabbitMQ and the topology service is connected over here. And once they communicate together, we can see the output, which is seen over here, which says a graph has been connected.
Moving on next, now we have the security RAP, which works in coinciding with the resilience app. What it does here, this is a modified diagram from the one you saw previously, where the node will be sending alarms to the AMQP server, where then the security app will analyze the alarm severity. So that means like, you'll probably get 3 warnings. So it's like, oh, there's nothing wrong. Oh, something might be wrong, or oh, something is really wrong. So what that's going to do is that's going to send commands back into the RAN network where it has instructions on what to do. It's like, you're fine, don't worry. You might want to keep an eye on it, and then nope, shut down completely, you're done.
Okay, regarding the spectrum management RAP or the frequency RAP, so basically being that the spectrum is a limited resource, it's essential to find a way to manage the topology across the available frequency channels in an effective manner. So spectrum sensing allows for real-time monitoring of the frequency channels and the frequency occupancy. If we could see the graph, maybe just click it one more time. Yeah, this is so the graph above represents the energy of the spectrum, while the graph below represents the estimated occupancy. So basically through our RAP, the RUs are distributed according to the available channels.
Leave it. Go back, please. So the spectrum sensing is done in GNU Radio, which is an open source software, and we use the energy detection method, which pretty much takes the energy of the received signal, it compares it to a certain threshold, and if the energy of that signal is above the threshold, the channel is considered to be occupied. So the communication between the RAP and GNU Radio is achieved through AMQP. And could you go to the next slide here? Here we have an example of what it's actually doing. So on the left here, we have the occupancy information that is being sent. On the left or right, we have that information being received and the topology being changed accordingly. So the red text actually represents the changed topology, that is the new frequencies that are assigned to the RUs. Yeah, that would be that. Any questions?